introduce Tobias Schaetz from Feshbach University, and he's going to tell us about some cool stuff with atom-ion systems. Please, Tobias, the floor is yours.
Thank you very much. Jesus already told me that I'm his first three-body problem today because I have the right trousers, but the jacket is missing that I normally wear for showing my respect. So next time, if there is one, I will wear it. Meanwhile, thank you very much, Jesus, and the organizers for having us here. I have the great pleasure to already, have the first lie on the first slide. I will not talk that much about optically trapping ions and atoms. It will be about atom-ion Feshbach resonances and three-body recombination in hybrid quantum systems. And here, hybrid means mainly lithium, barium plus, and in hybrid traps. However, just reminder to myself that there are other things we are looking into, and we are stopping ourselves from doing more in optical traps. And we recently had ions in optical lattices, and also sympathetic cooling in purely optical traps of ions with atoms. So we really want to pursue this too with great collaborators. We are working also with larger ion crystals, two-dimensional arrays. Let it be larger arrays in one harmonic confinement, where you see here some defects in the Coulomb crystal we love to play with. And we also want to keep, because here we have already these larger crystals. I wouldn't talk about scaling because this is a mathematical factor, so scale invariance, there's nothing about scale invariance. This is just trying to get to a larger size to see more physics. And here we are in one common potential for all ions, while here we create individual trapping sites in the smallest triangle you might think of, and trying to keep the control of the individual ions high enough, but the ions close enough to have strong enough long-range interaction to do some physics. And here you see one animation with the ions sitting in their individual RF traps. This is a surface trap at a distance of 40 microns. And I just discussed with Hussein today about possibilities potentially to think about the phonons that we had here tunneling between these lattice sites, while it were still coherent states at that time, but that we saw better and better coherence times the more lattice sites we filled and used. And this hints kind of a synchronization of these individual oscillators sitting here. It would be a pleasure to look more into that, also in linear chains. And here you see a more complex trapping surface where we have 13 individual lattice sites, a trapping hub up here for loading these individual sites where we can shoot the ions with high efficiency into their loading spots and hopefully take advantage of these longer range interactions. Okay, I don't want to forget about speaking briefly about these other endeavors of non-Markovianity and the onsets of thermalization in quantum systems. And we just had an open quantum system approach running within our ion trap with one of the godfathers of open quantum systems, Heinz-Peter Breuer. So this might also sneak in the context of our endeavor here with the Feshbach resonances. Looking at Feshbach resonances as some quasi-bound state coupled to a continuum of states, so this might give us some additional insight at some point. These are the heroes in charge in the Bali lab. And I want to explicitly mention Fabian Thielemann, who is now in Stuttgart with Tilman Pfau and Florian Meinert. Joachim Simund, who is the PhD postdoc, so to say, almost postdoc, running the experiment right now. Pascal Wegwesser, who is with Emanuel Bloch at MPQ in Munich. And Jonathan Grieshaber, who is one of the best master students I have, but he goes for a spin-off. And here we have the Michael Tomza and Krzysztof Czekminski, the current heroes of theory, collaborating with us, and others being present here, being mentioned in time when I go for the outlook. Okay. This is somehow the outline of the presentation. I want to briefly introduce to you barium lithium. We had the nice introduction of René already yesterday. So just pointing at some peculiarities of the barium plus lithium system, lithium-6 fermionic. I want to recap what we did so far with barium plus lithium in hybrid traps, with the lithium being not in the lowest ground state, but the first excited state, because life should be easier there, we thought. And well, since it was not, we moved to the lithium ground state. And once again, we were wrong. It's even more complex here, but I want to share this interesting or complexity or problems with you, and want to talk with you about how we try to characterize these Feshbach resonances that we observe experimentally and in collaboration with our theory friends numerically. We have a two-step model that should explain our three-body losses, and I want to share with you how we want to investigate the validity of this two-step model working with spin-polarized lithium ensembles compared to spin mixtures on resonance, off resonance. So combining these, checking for the dimer formation and the third participant just causing the three-body loss. And if there was time and not too many people leaving, meanwhile, I would love to share the dreams about optical trapping in the future. This is just a rush through it. As we heard already, this are RF electrodes and DC electrodes confining this blue spot here. Barium ions are blue. Lithium is red. Don't know why this is the case. Might be our camera. But we confine them together in this hypertrap, even though we can confine them optically too. And as we heard already, there is the secular motion that we see, so amplitude, motional amplitude over time. And there we see the secular motion, but if we are not at the RF node, we see these additional wiggles on the time scales of 1 over the RF frequency driving motion. When we talk about this here as a fundamental source of heat for heating the system, putting energy into the system, one should forget that there were wonderful experiments done in these hybrid states despite this trapping, and you know most of them, if not all of them here, and I for sure forgot somebody. Good that I didn't forget Rowie, so please hint at me whom I forgot even during the talk. Okay, so we saw also this formation. So we see here our ion. In principle, one could think about it sitting on the RF node at absolute standstill, temperature 0 as a point-like particle. So not affected by this RF micromotion, but if an atom approaches, this 1 over r to the 4 polarizing potential leads to a displacement of the ion from the RF trap, and then this heating mechanism sneaks in, does some also beautiful physics on top, but this is not what we are after. As René also stated already, one can cure some of the consequences by using large mass difference of the ion, ytterbium or barium, and lithium, much smaller mass, to reduce this displacement of the barium ion and also to get into the center of mass frame in a privileged zone where the kinetic energy of the barium plays a much smaller role. And I shouldn't forget here this paper that René also referred to with entering the quantum regime for the first time with buffer gas cooling in his group. Okay, with that, I would take you on the fly with the barium and the lithium too. And well, I'm an atomic physicist, not really a molecular physicist. This scares me already, but if this scares me, I should just look at the real calculations. It's even, I shouldn't call it messy, more interesting, most probably. But what we see here, this is one peculiarity of barium plus and lithium, that lithium in the ground state and barium plus in the ground state forming the, here's sigma singlet, sigma triplet states, form the ground state of the system, thus no charge transfer in this scenario. We have an additional challenge, nice spot. What you might ever call it is this crossing here with this triple pi state that, combined with second order spin orbit coupling, allows for coupling a lot of additional degrees of freedom. For example, also the coupling the different partial waves. So currently being one of the suspects being responsible for making our spectra even more interesting. Okay. Yeah, singlet, triplet, I think this is not to be mentioned here. Of course, are missing the centrifugal barriers. We will need this after introducing you or reminding you just very briefly what the differences are. We heard already, well, 1 over r to the 6 for van der Waals, for neutrals. And here we have our ion atom interaction, 1 over r to the 4, leaving us with different asymptotes, higher density of vibrational states, and well, if we talk about the length scales that are characteristic and the characteristic energy scales, we are in a very different regime. So the length scale is set by, again, the distance of the p-wave centrifugal barrier, and the energy scale is set by the height of the centrifugal barrier, as with neutrals. But here we end up with 8.8 microkelvin for the S-wave regime, so the height of this barrier to be well, crossed or surmounted. And then we have this typical length scale of 70 nanometers, what gives rise to these very long range potentials. Okay, so deeper look into the system and into our experimental setup. We have a single barium ion, as René with euterbium, is sitting in a bath here of spin polarized lithium-6 in the second ground state. I can elaborate on why the second ground state, but I shouldn't bother you with all these details. Please ask me later if you are interested, because this is a summary of 4 years or 5 years, I heard yesterday, most probably it's 5 years meanwhile, of tears, sweat, and frustration, but also some results. So I can't get all the experimental details, but perhaps some cornerstones. This is of the order of, at that time, 20,000 lithium-6 in state 2 at a temperature of a little bit below 1 microkelvin. This is 0.6 T Fermi at this level, with an atomic peak density of 10 to the 12 per cubic centimeter. We don't are as cool as Roy Oseri when he brings his ion into his ion trap. He used the forces or weapons of quantum information processing, or at least sideband cooling, to prepare his ions in the motional ground state. We have a very weak trap. That is, we rely on the thermalization within the first 100 collisions with the lithium gas to get in the collisional energy regime where we want to be, to then switch into this final configuration where the collisional energy in the center of mass is then of the order of 10 microkelvin. Most probably at that time already a little bit below, but we tried to be very conservative, not to get too much trouble by review. A key component is that we keep the stray fields very low, or compensate the stray fields with our tools that we have for optical trapping. Just imagine if you have an optical trap, it has a lot of advantages. René could add some disadvantages. But one advantage is that you are very sensitive to stray fields, and that is, if you can trap an ion optically, then you know your stray field compensation must be very good. So in this case, it's a tool for having good stray field compensation, and that having the ion very well centered on the RF node. Okay. Then we observed on the one hand side, this is something where I should cite Kettele. We do these beautiful experiments, and at the end we make all kaput. Yeah, this is this part. But here we also saw an enhancement of the sympathetic cooling rate, independence of the magnetic field. Here, well, hinting also at Feshbach resonances, enhancing the sympathetic cooling, so a two-body process, elastic. But we also have these three-body losses that I want to refer to a little bit more in detail. Well, not that much in detail, because Mikhail Tonza and Krzysztof Szekminski had a very hard time in supporting us to assigning these resonances, and it's not yet done. And they bring all in, so it's not that they wouldn't do a bad job, not that I could judge that, but discussing with experts, they are doing everything they can, and it's just very hard to explain why there are so many Feshbach resonances here within less than 100 Gauss. 13. Four were expected. Okay, there is this second order spin orbit coupling, making this Hamiltonian here much harder to treat, also numerically. So that was the point when we thought, well, then let's go to the lithium ground state, so even less energy, and this is what we did. So we went then to this lowest lithium state. And this is where, if I haven't taken out the wrong slides, where we should end up now. This is once again here for the configuration of searching for the Feshbach resonances. But we use an additional tool here, and this is using the barium ion in the D level, D3 state, to monitor or to probe the lithium density. We are not that much experienced in neutral atom trapping. We are ion trappers, and that is we didn't trust ourselves well enough that the atomic density, the lithium densities are well enough defined, and it's also not so easy for the single ion to really know where you are, to know what the local density is. So there's also beautiful work. I should talk about this too with Olivier Dulieu and his group on working with these excited states of barium and seeing avoided crossings and quenchings of excited states. Yeah, but here I will just talk about this lithium density independence of the displacement now of the barium ion. You remember we put a lot of effort in not displacing the barium ion because we want to sit on the Reif knot, but now we are displacing the barium ion. Okay, first of all, this will lead to an excess kinetic energy of the barium ion, and this is here on this other axis, and this will be our scale also for this additional kinetic energy in the center of mass frame. That's one thing. Forget about this here right now. Just think about it that if you lose the ions very quickly because of a single two-body collision, because this is an inelastic collision where you de-excite where we de-excite the ion or even lose the ion, and we can find it then in different states, then we know we probed a collision with a lithium atom. And these collisions are independent on the kinetic energy. That is why we can probe the density via this scan along y-axis, x-axis in our atomic cloud. And this is what we are finding here. And the nice thing about it is that we then can trust better what we get by absorption imaging, what people normally do to get the intensity of their atomic ensembles, absorption imaging. This is in agreement now, this absorption imaging, with the density profile that we get from our barium ion D3 level losses, giving us the hint or the chutzpah to believe that we really know well enough about the densities at the location of the ions. We went a little bit colder here, 0.5, perhaps even 0.3 T Fermi, a little bit higher densities, and well then we once again embed our barium ions into the lithium, but now in the S state, so in the ground state, searching for Feshbach resonances again. And this is what we observe. Well, if we now place our ion at zero displacement here, okay, it's already not at the center of the lithium cloud, right? Okay, this is at least we know it. We could correct it, but then so we have to correct it several times. That's most probably thermal shifts. But we can place either our ion here at zero additional kinetic energy, or we can displace our ion and add collisional energy and ask ourselves how huge is the survival probability of the barium ion. And if we do so, we find by scanning our cloud for different kinetic energies, collisional energies, that these experimental dots describe what other heroes of the field described with a semi-classical, classical picture of e to the -3½ energy dependence, and this is what would be expected. You might see this is the moment. You see here is an empty spot. Exactly, because if we enter into this regime where the additional kinetic energy is below 200 microkelvin, and this is in the center of mass frame, the P-wave barrier, if we enter therein, then first of all, this survival rates pop up, and then the survival rate drops close to zero. And well, this is a failure by 21 sigma of this description, and it leads us to the conclusion that within this energy window that shows us the very well done Tobias in yellow on white ground, well, this is the energy window of the centrifugal barrier of the P wave, and within this energy window, this occurs. Well, So we went for the spectrum and wanted to now really assign our resonances in combination with the work of the theoreticians, because everything should be easier. And this is the first spectrum we took. And we take out here one resonance, this one here. This is strange enough, it's not visible. This is this resonance because it's a little bit isolated. So we can very well resolve these resonances, but it's quite a bit, and we thought we are in a forest of resonances, and there might be a site less, so we scanned for 100 gauss and found 49 resonances. Well, on the one hand side, this is fun. I think Michael Tomsa disliked us for that, but he's still talking to us. And it's additionally looking very different to this channel 2 in lithium, so they are much narrower and more resonances, and this is also puzzling because this shouldn't be so different for these two lithium ground states. Okay, so as you see, Krishik is already a little bit more. He's still, so we are still working on it with Masato Morita from Japan, and experienced postdoc of Michael Tomsa, and they try to assign these, or also in combined forces with random matrix theory to explore the statistics of these resonances, checking for perhaps chaotic spectra. It doesn't look chaotic so far, but I can elaborate more on that, even though this is ongoing work. Okay, that's not the end. How much time do I have left?
5 minutes?
5 minutes only?
No, 10.
Thank you.
Only for you.
You are my personal Jesus. Yeah, this is an 80s joke. This is how the 80s, sorry. Okay, so this is not the end, because then we thought, now let's run the power of the, yeah, okay. It was the time when we thought, now let's play with our energy dependence and see what this resonance does. So we are shifting our ion out of the center, calibrating the kinetic energy, so the collisional energy of the system, and ask ourselves what happens to our resonance. And here, this color code that I personally hate, I hate these color code. You see here in 0 additional collisional energy up to 0.8. 0.8 is now calibrated as the P-wave barrier. And if we climb up in the collisional energies, we see that the resonances get shifted, broadened, and already below the S-wave barrier, a P-wave barrier, they close to fade away. Well, one might think that this should be an S-wave resonance. This is, I learned a lot also out of the work of the neutral atom people, or having also seen this broadening and shifting of resonances. This doesn't mean already that you have an S-wave. It's just a low partial wave, could still be a P-wave. And even though the barrier is much higher, but these Wigner threshold laws lead deep into these, these states open for tunneling. And so, well, we analyzed what we had, and there we combined a two-step model to have a quantum recombination model to compare what we would expect from the different partial wave resonances. And, well, this, in comparison with our quantum recombination model, gave the best agreement with an S-wave. P-wave is not absolutely included. We compared the chi-squared values, and it's twice off, so to say. So these are the S-wave, and these are the P-wave simulations or calculations in this context. A little bit more about this in the context of this two-step model. Okay. Well, after that, we thought, what happens if we sit now on the background? So you see, there's not so many, well, okay, here's a little bit of background, or here's also just a side background. The reason why we didn't went here is we didn't want to shift so far with the magnetic field crossing a lot of resonances. So just staying close by, having this resonance as a reference to see, we are still doing our things as we calibrated them, and then we go on the background. And here you see the same temperature evolution or collisional energy evolution again. We start with background, so this is survival probability close to 1. This is when we get off here with our additional collisional energy. And with the collisional energy increasing, we see that there rises our Feshbach resonance and then fades away again. And this occurs here. This is roughly three times the P-wave barrier. So this fades away pretty early, so quite deep. I would have expected, being stupid, that this needs much higher energies. But once again, with the Wigner threshold laws, this is also what neutral atom people experienced or observed. Please correct me if you disagree. And here we see, once again, our recombination model describing, this is not to be in quantitative agreement, but in qualitative agreement, also that resonance arises and fades away with a broadening and shifting. Okay. With that, I think I get you briefly in our two-step model that you all know much better than I do. I learned it's a Lindemann-like model. I thought this is a band from Germany that I know. So I got in contact here because our theory friends told us to do so, and we had very beautiful onsets of discussion with Paul, Jesus, Jose, and Panos already, and ongoing discussions to see how well we can validate whether this two-step model is applicable to our system. And well, there is this dimer formation rate that you might have expected, and then there is this rate of additional collisions with a dependency on the density of these additional, the atomic density allowing for these additional collisions. And here in this dimer formation rate, there's a C-2 factor that takes care of the Wigner threshold laws and forming then this dimer formation rate and giving us here such a bright Wigner formula with a certain width, so width defined of the resonance by the losses, so giving me some intuitive picture what occurs here when we get cross sections and derive loss rates out of it. And this was in nice agreement, as I showed you beforehand, but now we wanted to know better, is it really two-step or is it perhaps one-step and the three particles? And for that, we add a spin mixture to the barium bath that is either having complete state 2, state 1, or something in between. And here you see the barium survival rate once again, independence of the magnetic field. Here for the lithium being prepared in state 1, our resonance again, and here in lithium in state 2, so pretty much offset. So not resonant interaction with the lithium being in state 2. And well, now our Lindemann-like formula has to be adapted, and this adaptation now must include that this process is allowed to be done by either lithium 2 or lithium 1, because there is not resonant behavior required. But here we need still our dimer formation rate. That is, here we have to multiply once again with the density of lithium 1 for the dimers to form. And also here we have to take this into account and in such a way that we now take here not densities but fractional densities or fractional atom numbers. So this will be, because we are working with lithium in state 1 on resonance, divided by lithium in state 1 plus lithium in state 2. We can keep now, for example, the total amount of atoms constant and just play with these knobs here to change the amount of contribution. And if we do so, we see here this is the loss rate on resonance, and this is this sorry, this is too small. This fractional, it's preliminary. This is first time that I show this. And what we could see here is a linear fit, preliminary linear fit. This would mean here all of the atoms are in lithium state 1, and here all are in state 2, thus here no barium dying, and here the largest rate. But this is why I show you this very preliminary curve, because one might think this gives us a hint already that this K1 and K2 factors might be different for the two states, and also that the Pauli exclusion principle already might play a role for higher atom numbers. So what we are doing currently is also increasing the absolute atom number and playing with these parameters to see how well we can derive what kind of rates are at work here. Okay. With that, I'm with the dream part.
You can dream.
Oh, yeah. Okay.
For now.
Okay. Then I do a quick dream. What we want to do now is we want to assign our Feshbach resonances by experiment and see how we can potentially assist theory to assign the resonances also in theory. It might be that getting colder is helping us. It might be that random matrix theory is helping us, because it might be that you think you don't have chaotic spectra, but it's just the overlap of many spectra, and by that you're ruining the statistics. And it would be very interesting to see what character of the Feshbach resonances are there, to see whether this is an overlap of different spectra or one spectrum. This spin mixture and spin statistics play with the two-step model I already dreamt of. We have an additional feature now. We have a clock laser that can drive in barium the S to D transition. It's called an optical qubit for some people, clock transition, because it's a very long lifetime, more than 50 seconds. Nothing against the terbium from René, but for us, a very long lifetime. And by that, we could start the motional state analysis that we normally do in our other labs with the quantum simulations to analyze the Fock states, for example, red sideband to blue sideband, seeing how cold we are in this regime and also what kind of distributions we have. We could take advantage of the state-dependent optical confinement in the optical trap, so playing in the RF trap with changing the confinement of the answer. What should that mean? Well, for the optical trap, it's important in which electronic state you are to know which Stark shift you have to define the confinement. As we learned from the RF traps, there it's just charge to mass. That is, by shining in with light on the ions and atoms, we could make this now electronic state dependent. And also, well, there are proposals of Giovanna Morigi where you have a linear string of ions, but if you weaken the confinement, for example, for one species, you get a zigzag structure. And if you do a quantum superposition of both, you see this is the dream part. Open quantum systems might help us to describe this coupling of the quasi-bound state to the continuum, and there we hope also to learn a lot from our theory friends and thinking about T1 and T2 star times of our barium ions embedded in this lithium being disturbed in phase or in spin flips would be very interesting for us. Here I should have said, in the future, we don't want to shift our ions around anymore. We want to keep them where it's coldest, but we want to shift our degenerate gas over it. And if we do it with constant velocity, we might be capable to probe really the partial waves with a very narrow energy window. Dream part. What we want to do in addition is, now that we are potentially that cold, we want to see whether we can enter the regime of polaron physics, where we tickle the ion, for example, in absence of the lithium atoms, and then we see that we have a certain secular frequency of the ion, and then embed it in the lithium, and then hopefully see a change of the oscillation frequency, hinting at an effective mass that we get. So tracking the, or having the impurity now addressed by its environment. And this is also in collaboration with Krzysztof Szekminski, who has a proposal out there that I still have to understand completely, or at least sufficiently well. And here, talking about these multipole traps, we have in principle an 8-pole trap on top of our quadrupole trap in our trap. So when we go purely optical, we might have a box potential with not a lot of micromotion. In the center, our optical potential for confining our atoms and ions all optically. But if then there's a product state arising and a molecular ion is formed, we might keep it in this box potential and then reconfine it and see what the leftovers are, what we normally wouldn't be capable of doing with our purely optical traps. And with that, yeah, okay, this is too much streaming. That would be our two-color trap where we trap rubidium, barium. And, I should go. Tobias, stop. I want to end with this, once again reminding of the heroes of the real work, and thank you very much for your attention.
Time for questions. Please, Liv.
So you are already sort of in a quantum genesis regime from the time.
Mhm.
Lithium, right?
Mm-hmm.
So, and don't you think that there's some effect of this quantum mechanics on the formation of clusters? Some of the Polaron that always exist in storage, just because you are always in quantum mechanics regime, so probably your three-body sort of affected by this effect.
Would be very easy. Then we should see a deviation of this two-step Lindemann-like model, right? This is our hope, that we see that we can follow the Lindemann-like model for a certain while, and then we get deviations, hopefully.
This is not what is happening now.
Well, right now we are not, so what I showed, and this is why it's preliminary, is, in principle, I'm afraid to say this, but I think we have so many open parameters that we can fit the elephant. So we have to have a more broad data range to be really sufficiently convinced of our own fits. But we don't see a deviation right now that hints toward it. But we see an influence of the Pauli exclusion principle. Very preliminary.
Yeah, you mentioned this triplet pi set in the very beginning.
Mm-hmm.
Is that the one responsible for the Feshbach resonances, do you know, or are these different type of fine potentials?
No, this is a very good question. So this, normally the sigma singlet and sigma triplet wouldn't couple. But due to the coupling of the triplet sigma with the triplet pi, you get also a coupling between the triplet and the singlet that it's sigma. And this then allows for additional terms in the Hamiltonian that brings you in. All of a sudden, I didn't know about it, but you have already spherical harmonics. This is for you completely normal in molecular physics, but now in the operator and not in the state. And this is allowing for this mixing in of angular momenta, giving us combination of partial waves, so S and D. And today I learned that perhaps S, D, and G, right? Never thought that much up. So yeah. So and it's just a mixing. It's not that the energy would be that high. It's just the basis is renewed.
Just to comment on the triplet pi coming down, it has a relatively sparse density of states compared to the very narrow energy range of the optical. So, the open question would be whether one of those accidentally is very close to threshold and causes all kinds of strange stuff, or whether they're all fairly removed from threshold. So that would be something, if the spectroscopy of that state were known a little better, and maybe know whether there's an actual level there close enough to cause perturbations of a major sort. That's an open, unknown question.
I had a beautiful lunchtime with him kicking me.
Yeah, so when you have fermions, the threshold law should change from a constant K3 at a given, say, magnetic field to linear in K3. Can you study this energy dependence? Just pick one field and study the threshold law?
I hope so. It might be in there, your assistance might be highly appreciated, because right now we are picking on a very narrow resonance, and there our thermal distribution is already quite broad compared to the narrow resonance. So it might be advantageous to go for a broader resonance to do that, but we had all our hands full so far. But that would be very cool to know what kind of resonance, partial wave width, would be advantageous to do so, if that was possible.
So, Tobias, do you know why, if you increase the excess micromotion, that it shifts? Can you explain it?
This is no. So this is not, let's say, our explanation, but the explanation that the neutral atom community gave. So this has to do with the threshold, partially also because of our energy distribution broadening. So we are not having this delta peak in collisional energies, but our collisional energies broaden. And then we...
But it's almost kind of like two delta peaks, because then you drive it, right? So you get this kind of double peak energy.
Oh, well, please help me, double peak.
Because you give it excess micromotion.
Yeah.
Right? So the energy distribution kind of looks like
So I was still thinking about getting from at low collisional energies. We are still very well described by our Boltzmann distribution. I think this is also what you wrote in your nice review article for very low temperatures. And if we get high, we get this long energy tail, this Thales distribution. What you are saying now is...
Ah, I see, yeah. So you say it's completely, okay. So it's completely mixed by the buffer gas cooling, because it's not like you switch it on like temporarily, but you have it on all the time.
Yeah, right.
Yeah.
And I wouldn't be brave enough to just state this, even though I try to forbid my students to do all of these Monte Carlo simulations, because that keeps them for 1 year out of the laboratory. But this is confirmed by the Monte Carlo simulations, the brave Fabian Thielemann did with...
Yeah. So I was just indeed confused by my own experiment, because we did not do it. We only did it during the spin exchange, that we switched it on. But of course you did. I agree completely.
Thank you.
So, in our community, we just, realized that it's a nice tool to see the Feshbach resonance by losses, that it's essentially a very crude one. And then we just come to the conclusion that the best way to describe the resonance is just to go and measure the cluster of the dimer that is produced on the positive scattering region, and that gives you significantly more precise information about the resonance.
We have one dimer.
Yes, but still, it's, well, you have one ion, and the dimer is also charged, so...
Okay, this would be, if we took, for example, a multi-channel plate to get it out, we would have to know when, but that could, is this what you're referring to? Because the molecule is dark, so the dimer is dark.
Yes.
And
well, it's very weakly bound data, so especially close to the resonance, it's extremely weakly bound. So it's probably not that fast goes away from the spectroscopy. So even spectroscopically, you can still see it because it's a deviate from zero energy. It goes down by few megahertz, kilohertz. It's really binding energy, which is
okay, are you referring to shifting with the magnetic field towards a molecular bound state and then doing RF spectroscopy of the state? Yeah.
You should associate that somehow.
We tried it, but we didn't. Now I understand what spectroscopy for me. I don't know if you said it, but with the microwaves, we could see that we get into a deeper bound state and then dissociate again. But we didn't see the signal. So we tried to get there and come back, but we weren't capable of coming back with the ion. You know, if the dimer is formed, we should be, if it's a coherent process, we should be capable of coming back and seeing the ion. But 2 thumbs were not enough.
That's probably not a collision that makes decay the whole system to a deeper bound state, so probably not have enough time.
Might be, or that perhaps also the micromotion is not advantageous. But please continue thinking.
I work hard.
Any more questions? Please.
I'm just thinking randomly out loud. So if you have made, the recombination is pretty fast, right? These resonances. Once you make a dimer, isn't it very fast to make a trimer too? Got an ion, it likes to grab neutrals.
Yeah. So you were talking about this process of stabilizing the trimer and keeping a trimer, because if not, we can't. So.
Well, I was just wondering, like, perhaps some of the substructure or the plethora of resonances, could some of this reflect more than 3 bodies?
I would have to ask an expert on that. I don't. That is interesting. Yeah. Perhaps I'm. Yeah.
Just a
Mhm.
Any more questions? I think no. Thanks, Tobias, again.
Thank you very much. Thank you.